Thanks for joining us today for the Fundamentals of Measuring Dissolved Oxygen webinar. I'll be introducing you to your presenter, Colleen, here in a moment. But as people are coming in and joining us, I just wanted to go over a few housekeeping items. So we are going to be answering questions during the session, and we'd love to do that. So either use the Q&A feature or chat. We'll be monitoring both of those, and I'll be passing those along to Colleen during today's session. And you'll also get a link to a shared folder that includes additional resources for you. Right now there is some experiment files, the certificate of attendance, and also the slide deck for you guys to reference. And so again, feel free to put your questions in chat or Q&A. We will be answering those along the way, and we are recording this session, so everybody will also get the recording in a follow-up email. So with that, I will pass it over to you, Colleen.
Hi, good afternoon, everybody. I hope everyone's doing well today. So let me start sharing my presentation. So today we are going to talk all about dissolved oxygen. Primarily, we're just going to do kind of a general talking about the fundamentals of measuring dissolved oxygen, doing some tips and tricks and best practices for data collection today. So my name's, I'll do my introduction here in a second. It's been a while since I've done one of these. So today, pretty simple agenda. Introduce myself. We're going to talk about what exactly dissolved oxygen is, different methods we can use to collect it, best practices for data collection, and I'm going to definitely cover some troubleshooting and sensor clear that I seem to get a lot of questions about in tech support, and any other general questions you might have about using dissolved oxygen probes or measuring dissolved oxygen. So my name is Colleen. If you have called in and had questions about biology or environmental science, there's a really good chance that you talk to me. My background is I have a degree in biology from Truman State University, which is in Kirksville, Missouri. I received my master's of science in science education at Montana State while I was teaching. And my background's kind of different in that when I graduated college, I went on to actually work on a PhD to become a research scientist, and realized during that process, I much preferred thinking and talking about biology as a global thing instead of looking at little microcosms. So I actually dropped out of my PhD program and became certified through an NSF grant, and started teaching in a high school in Houston, Texas for 6 years, where I got to teach biology, pre-AP biology, and my favorite class of all, AP environmental science. So today's topic is dissolved oxygen. And one of the questions I'll get a lot about is a lot of people don't fully understand or comprehend exactly what dissolved oxygen is. So when we're looking at a measurement of dissolved oxygen, one, we're looking at what amount of oxygen in water. So we're not talking about oxygen gas that's in the atmosphere. We're specifically referring to aquatic environments and looking basically at oxygen, O2, that has been dissolved in water. And that's why we're talking about, usually when we do measurements, we're talking about them in milligrams per liter, because we're looking at the actual concentration of how much oxygen is present in the water. Now, the two primary places that oxygen comes from in water is going to be primarily photosynthesis. So you've got aquatic plants, you've got plankton, you've got other microorganisms in there that are going to be adding oxygen to the water column as they're doing this process of photosynthesis, very much like plants on land are adding oxygen to our atmosphere by them doing photosynthesis. The other place that oxygen can come from is diffusion. So basically diffusing from the atmosphere into water. And that's going to be typically due to like wave function, ripples or riffles within streams and rivers. So those are going to be our primary things. Now, a lot of times we are looking primarily at concentration. So how much can the water hold? And a lot of people get that confused also with saturation. So saturation and concentration are actually, they're both measuring the amount of dissolved oxygen, but different aspects of it. So concentration, we're looking at how much actually is present in our water sample at that moment. While saturation, we're looking at what point is our water, let me rephrase that, at how much does our water actually have the ability to hold on to when it's fully saturated? So, for example, water that tends to be at a warmer temperature is going to have a little bit of a lower concentration of oxygen in it when you do your readings. So warmer water, you might see a reading of 7.1 milligrams per liter. And the saturation could still be 100% there because that is fully saturated at that temperature. But as we lower the temperature, the concentration, the amount of oxygen that the water can hold on to increases. So it might start reading 9.1 milligrams per liter, yet it still could be 100% saturated. And that's all this kind of weird relationship between temperature and the amount of dissolved oxygen that water can hold on to. So a lot of times we have to talk about why is dissolved oxygen so important? Well, it's very much the same as why oxygen is important for terrestrial animals. Aquatic organisms like fish need to be able to breathe. And I say breathe in a very generic, loose term, because they're going to be extracting the oxygen from the water to actually be able to do cellular respiration. And the same thing goes with a lot of other organisms too, that they're going to be taking in oxygen from the water through diffusion. And so if we don't have enough oxygen present in the water, organisms are not going to be able to survive. And this lovely image graphic that I kind of made on Microsoft, or not Microsoft, Google art design, whatever it is, kind of shows you the range that we typically see of dissolved oxygen concentrations. And so there are specific species of fish and other organisms that are going to be finding their niche, and they have to have a certain amount of oxygen present in the water to be able to survive. So for example, if your water concentration is 6 milligrams per liter of oxygen, that's not a really great level. Your fish are going to start to be a little unhappy and stressed. And anything below that, you're going to see population numbers start to decline. And the type of organisms are going to kind of change over to be a bit more of those bottom feeder organisms, bacteria, things like that. While if the higher we go, we tend to see different types of fish populations. Specifically here in Oregon, we're always talking about trout or trout fishing or salmon, and they like really high oxygenated water. So you're going to tend to see their oxygen levels up here to 10 to 12 in those types of environments. Now, once we get kind of down below 5 to 4, 3, 2, 1 in the milligrams per liter, that's where we're going to start to encounter aquatic dead zones. And these are going to be, we're starting to see these become more and more common because of processes such as eutrophication and excess nutrient dumping that's happening at, say, the mouth of the Mississippi River. So we're starting to see these large dead zones happening because the amount of nutrients coming in is causing bacteria to increase and other organisms that are really fast decomposers that are actually taking oxygen out of the water, so nothing can actually survive in these areas. So understanding how the oxygen gets in the water and the process of it is actually some really important concepts. So how exactly can we measure dissolved oxygen? Well, when I was teaching, I was using more of these chemical methods. So a lot of people might know of like the SNAP chemist kits or our lovely Winkler's method. So these different methods are great, and kind of the very, especially with the chemets one, is kind of a quick and dirty way to be able to get a quick oxygen measurement of water. But the problem with these two types of methods is going to be the amount of waste that you collect from them and the availability of being able to do it easily and simply, especially in the field. Both using colorimetric and the Winkler's method or titration method is going to require you to actually use up some of your water sample. And so if you're saying measuring eco columns, your volume of water in there is kind of limited. So if you take water out, you're going to have to add water back in. The other thing that I found when I was teaching AP Environmental is I didn't like the amount of waste that these chemet kits were producing. So I was constantly going through them. And I mean, if they come with, I think it's usually like 10 or 12 ampules, and I could go through one set of those in a class period easily. So it gets really wasteful. And then the cost of replacing them seems low, but cumulatively definitely adds up. The other two methods to measure dissolved oxygen we have are electrochemical and fluorescence. So electrochemical method, there's two different types, but primarily this one here, if those of you who have used are what I now refer to as the old school Vernier dissolved oxygen probe, might remember you have like a platinum electrode or silver electrode in here, and then you have this gas permeable membrane. You have to take off the bottom cap, fill it with a filling solution, put it back on, then the probe has to warm up for 10 minutes. And for best results, you have to make sure to calibrate it so that it's calibrated based on your temperature and pressure to where you're located. One of the things about this is that it can be a very accurate and give you really, really good readings. The problem though is that warm-up time and the calibration process with it is not a simple process. The other aspect you have to worry about here is with the tip here, you have this gas permeable membrane, and the reaction taking place to give us a DO reading is actually consuming oxygen. So you have to constantly be moving the probe around to constantly getting basically a reading across the membrane that has enough oxygen. Because if you just leave it in one spot and don't move it, your DO readings are going to start dropping because of the amount being consumed in that area. Then we go to our fluorescence method. And this is kind of the method that it's kind of what we consider the newest and greatest technology that has come out with dissolved oxygen readings. It's been around for about 20 years now, but has only been really accessible for consumer market for about 10 years. And so with these probes, there's no consumption of oxygen taking place. There's no warm-up time. We have a way that you can kind of reset it, but it actually can use onboard temperature and pressure sensors to automatically adjust the readings based on what it's detecting in the area. So this is kind of the new way that I highly recommended people towards going to, because unlike the chemical method, you don't have to use up a water sample. You don't have any chemicals you have to worry about, which you see in the chemical method and in the electrochemical with the filling solution. And you don't have warm up or calibration that you necessarily have to do to get it functioning and running. So those are kind of our different technologies and availability out there to do dissolved oxygen readings. So one of the things we get a lot of questions about is how can I improve my data, or I'm getting really weird, bad data. And the number one thing that I recommend people to have is absolute patience. You gotta make sure that you give it enough time to really reach that equilibrium stage. So because dissolved oxygen is so temperamental on and really tightly related to air temperature and water temperature, you have to think about, okay, if I'm taking a water sample from a stream that is reading 11 degrees Celsius, for example, because a lot of our streams here in Oregon are around that temperature, but my DO probe has been sitting out and is in air that's like 70, or probably, let me do my Celsius here, around 32, 35 degrees Celsius. That's a big temperature difference. So it's going to take a little bit of time for the probe, once you put it in the water sample, to actually do all those calculations and kind of come to a happy equilibrium point that's going to give you a pretty good stable reading. So patience, patience, patience. That is the number one thing I recommend people with dissolved oxygen. Some things for specific experiments. So when you're looking, the most popular experiment people do is looking at the relationship between dissolved oxygen and temperature. The number one thing that goes wrong with this is I talk to people who are taking a beaker of water and they set it on a hot plate and are just measuring the water dissolved oxygen as the temperature heats up. And they're like, it's not changing, it's staying the same. Well, that's because have you introduced any oxygen or allowed any oxygen to leave by diffusion with a beaker just sitting there? And the answer is no. The key for doing a comparison with dissolved oxygen and temperature is to shake, shake, shake. You've got to shake the water sample. Because what you're looking at is you're looking at that relationship of what is the temperature of the water and how much dissolved oxygen can it hold. So typically what I tell people do is you want to start with ice water, and you're going to pour that into either a water bottle, soda bottle, distilled water bottle, milk jug, anything like that, that students can then sit there and shake. And so as they're shaking, what's happening is you're basically imitating what happens in rapids in a stream, is you're introducing as much air and oxygen into that water through diffusion that it can hold on to. Then you're going to pour it out, do your measurement. Again, patience, you got to let the probe come up with the temperature right. Then you're going to repeat the process. And the idea is that as the students are shaking the water and the friction of the water moving around in that bottle, along with the heat of their hand, is slowly warming it up. So they do this through different steps and are going to get a different temperature and concentration reading for each step as we go down. Then you're going to repeat the process, but this time pour out half the water and add in warm water. And now you're basically going to start from warm and let it cool as you get up again to around room temperature. So the key is you have to agitate it. You have to shake to get the agitation and get that diffusion happening so oxygen is introduced into the water sample. I'm going to take a drink quick, and I see we have a question. So Matt asked, regarding the Go Direct probe, is the pressure measured atmospheric and the temperature measurements from the aqueous environment? Yes. So on the Go Direct probe, the pressure sensor is actually located right here and is more atmospheric reading. And then the actual temperature reading is this metal ring right here around the probe. And that's going to be what's detecting temperature. So right now it's going to be measuring atmospheric temperature, but when I put it in my water sample, it will be measuring water temperature then. So the other question, I actually just had this question recently from a customer here about photosynthesis. So I threw this picture in because it's kind of hard to visualize and talk about it. But you can actually do photosynthesis measurements with our dissolved oxygen probe as long as you're using aquatic plants. So in this picture, we have an aquatic plant called Java moss. It actually is a moss, not an algae, and it's in a bottle of water. And so what I can do is actually, what you can do is wrap the bottle in foil, allow the dissolved oxygen to go down because of cell respiration taking place, and then unwrap it and have a light shining on it to encourage photosynthesis. But kind of similar to the dissolved oxygen temperature one is that if your water is static, you'll notice when you ever do aquatic photosynthesis, you'll see the little air bubbles are forming along the plant as that gas is being released. But if you don't agitate that water, all of those gas bubbles are going to stay closed and actually not quickly dissolved in oxygen. So in this picture, what's hard to see is we actually have this on a stir plate with a stir bar at the bottom. And slow stirring actually is enough to help agitate it and break up those air bubbles to get a really good dissolved oxygen concentration in there that you can read. And it gives you a much more stable one, because what can happen is if you don't have the agitation, you accidentally like knock the bottle or something, your dissolved oxygen reading might be low and then it'll suddenly spike up and then kind of come back down a little bit. So this is a way to get much cleaner, prettier data. Another key we find is using an LED plant light. So it's hard to tell, but in the picture you can kind of see there's this pinky kind of glow to it. So this lamp here is actually an LED plant light, and the LED plant lights are just little LED bulbs you can get off of Amazon for pretty cheap now, that have mostly red and blue LEDs in them, along with some white ones. And they're optimized to help with photosynthesis. And we have found that they are fantastic at this because, one, they're the right wavelengths to encourage photosynthesis to take place. And two, because they're LEDs, you don't get a heat effect like you do with halogen bulbs or regular incandescent bulbs. LED plant lights, I swear by them now. Okay, just gonna look over here. Sorry, Angie, I'm reading the chat because I see questions coming in. So Robert asked, can the Go Direct probe be used to get a temperature and or atmospheric pressure reading since it has the sensors? Yes, it can. So I was going to talk a little bit about later about the differences between a Go Direct and a non-Go Direct probe. And one of the key differences is that it has the ability to be essentially what we call a multi-sensor. So you can use it to measure the dissolved oxygen concentration and saturation at the same time, along with temperature and atmospheric pressure. And Matt, yes, you can do this experiment with microalgae as well. You don't have to use an actual plant. If you want to use algae, that's a great way to do it too. Can I use geodim with marine green blue crabs? Yes. So we actually, on the Go Direct dissolved oxygen probe, we actually have a DO salinity channel. And what that means is that it has an equation in there because the amount of dissolved oxygen isn't as clean and cut as it is in fresh water compared to salt water. So salt water, you have some ions in there that cause the readings to be a little different. And so usually there's an equation you put your dissolved oxygen reading in to correct for the salinity. But on our Go Direct oxygen probe, you turn that channel on, you enter what your salinity is in PPT, and it automatically does the correction for you and does that readout. Yes, Lauren, you can do this to compare LED color and dissolved oxygen. That's actually a lab I have done with regular spinach leaves terrestrially, and I don't see why you couldn't do it with aquatic plants as well. Very good questions, everybody. Thank you. I like when you ask questions. So a couple more best practices for data collection. One of the probably more common things is that we're going to do a lot of dissolved oxygen reading when it comes to water quality. And when we do water quality, my kind of weird mantra with it is fresh is best. Because dissolved oxygen is so affected by temperature and pressure, it really is absolute best to get that dissolved oxygen reading on site. So doing it either directly in the stream, directly in the pond, or taking a sample and measuring it right away. And that is because of that temperature factor. Now, when you do, for example, the Winkler method, doing titration, that can be a little more difficult because you have a lot of chemicals you're working with. So I know when I did the Winkler method with my students, we would do the first couple steps where we had fixed the oxygen in the water. It's been so long since I've done it, I forgot which part of the step it was. But we basically fix it and then take it back to the lab and finish doing our titration there. If you can't do the measurement on site, that's okay. There are methods that you want to follow though when you get your sample. The first thing is you want to make sure whatever bottle you're getting your sample with is one, completely airtight. It does not allow oxygen in or out. And the other thing is you want to fully submerge that sampler into the body of water and actually cap it underwater as well, because you want to make sure there's no air bubbles present. If there are air bubbles present, it's going to increase the likelihood of you losing some oxygen by diffusion. The other thing you want to make sure is to actually keep it chilled. Now, the problem with all of this is when you take the sample away, you aren't going to have that temperature variable anymore to be able to get the true dissolved oxygen temperature of the water, or dissolved oxygen reading the water. But the key is you need to keep it chilled, and you want to take the measurement when it is chilled. And the reason is, as soon as that water starts to warm up or change from its environment, you're going to start getting decomposition take place. Because while a lot of people don't think about that water sample is going to be filled with bacteria and other types of protozoa in there that are going to start going through the process of decomposing and breaking down any organic matter that's in the sample. Basically, for those that do water quality testing, this would be the biological oxygen demand. So you want to make sure that you stop that process, because it's going to further alter your results of what that DO reading is. So by keeping it chilled, you hopefully will slow that process actually down. Okay. So Lauren asks, if doing this as a simulation in a lab, what type of water is best? Tap versus distilled, etc. And Lauren, can you clarify if you're talking about water quality or a different type of simulation from what we are discussing with? To show temp versus O2. You honestly, tap is going to be fine. Distilled water is great if you have it. If you don't, I've personally used tap water and have not had a problem with it before. I'm also a true biologist, not a true diehard chemist. So chemistry people might think otherwise, but if we're just measuring just temperature and oxygen, tap is fine. So moving on from water quality, going on to like primary productivity, and same thing with biological oxygen demand. Kind of the same ideas here. You want to make sure that you don't have any bubbles within your sample containers, that they are oxygen tight. And when doing primary productivity, again, I highly recommend doing an LED plant light just to ensure that you get the best results possible. It's really the advent of those and them becoming very affordable, I think, has been a game changer in getting really good photosynthesis data, both aquatically and terrestrially. Okay, so my busiest slide of the presentation, and this is probably where we're going to talk about the most. So, troubleshooting processes. One of the questions I always am getting is, why won't my reading stabilize? It's going all over the place. And usually when somebody says going all over the place, it's going from like 8.5 to 8.0. That's okay. You're going to see some variability in the readings when you're taking a reading. And that's just primarily because these are electronic devices. You are going to have some electric noise going on in place. There might be some agitation going in the water. There's a lot of factors. So one of the things I always do when I do data collection with water quality and water reading specifically, is I usually count down from 5, because over time the readings will pretty much stabilize, but they kind of might do this like little wavy thing where you're seeing kind of jumps back and forth in either the tenths or the hundredths place. Honestly, just kind of taking your best guess and having students record when they feel as that's the right value and it's not greatly changing upwards or greatly changing downwards. That's one thing to consider with that. The other thing with why won't it stabilize? Patience. Remember, patience. Again, you have to think about what the temperature of your water sample is and what is the temperature the probe has been sitting at. So if the water is really cold or really warm compared to where it's sitting in the atmospheric temperature, it's gonna take some time. It could take sometimes, I have found it in real extremes, 3 to 5 minutes before it really stabilizes. And that, like I said, is going to be in that extreme manner. The closer you are to what is room temp or atmospheric temp, the less time it's going to take to stabilize, because again, remember, our sensors have this temperature aspect to it that they're constantly getting that reading from and helping correct the DO reading for the temperature. One other common question is, why are my readings all over the place? If, you know, Susie's getting a reading with her sample that's 8.5, Johnny's getting a reading that's 8.8, somebody else is getting a reading that's like 8.2. Those are all within the general same range, so it's okay. Now, if you start to see readings where somebody is getting a reading of like 9.2 and like 7.5 milligrams per liter, that's a bit of a bigger difference. My rule of thumb is within 1 milligram per liter, it's pretty good readings because these are not research-based equipment. If you start going over that, that is the time where you might want to consider resetting the probe. And I'm going to kind of go over that a little bit after I'm done with the presentation. But basically, when you reset the probe, you're bringing them all back to a central number that hopefully will get them all back within range of each other. And this can happen over time as the tip of the probe starts to age. The other thing when you're troubleshooting is to look at the data and see if the data makes sense. So sometimes you might get readings that you're like, you know, that number, that 4 milligram per liter, that just doesn't seem like the right reading for my probe. So a couple places that you want to look at is when the probe is sitting just in its bottle here and you should know it has a moist sponge at the bottom of it. What exactly is it reading? Based on the temperature, it can be kind of anywhere, but between 7 and 9 is usually where mine's reading milligrams per liter. The other thing to look at it is what is the percent saturation. So these probes are set up so that this chamber here you can use to create a 100% saturation environment. And it's kind of a weird way, but that is going to be how we reset the reading on there. The other thing that you can do to check it is if you have just a basic aquarium bubbler. Oops, went forward, too far back, there we go. The way that I actually test probes here in the building is I set up a beaker of tap water, and I have a little $5 aquarium bubbler that I sit in that tap water and let it bubble. And basically am creating 100% saturated and concentrated environment. And then I go through and measure my probes to see what they're reading. And if they're not all reading within the same area of each other, then I definitely tell our department or our production department something's wrong with these probes. So it's a really simple, easy way just to kind of check and measure and make sure the probes are functioning properly. The other thing you can do is, and this is usually if you call me for troubleshooting that something's not right, the first thing I'll tell you to do is actually take your probe out. And for the Go Direct one, I'd say put your hand around the bottom of it, because then you're going to be adding heat to this ring. And what we should see is the dissolved oxygen readings start to drop because of the heat is telling it it's warmer, so your concentration can't be as high. If you have the BTA version, so our plug-in version, there is a metal dot here, and you just put your finger on that metal dot and it does the same exact thing.
Hey, Colleen. We just hit on one of the questions that we had in chat, but just to let you know, there's a few questions out there, but you specifically, I think, just answered one of them.
Okay, perfect. Yeah, so I just kind of answered Robert's question there. Is holding the direct probe, will the warmth of their hand have an effect? So it can, especially if they're holding it down here. Up here, there's not going to be any effect on the warmth of their hand. It's all about this metal band right here. And I have been able to get it to actually change just based on the warmth of my hand around the storage bottle. Luckily, usually their hand's not in that location when they're doing actual readings, so it's usually not something we have to worry about so much. Matt, can that be seen in the graphical analysis data table graph plateau? I'm assuming you're talking about the stabilization kind of readings, and you'll see what will happen is as the graph goes up, it does kind of reach that plateau and kind of goes around like this a little bit. But you definitely can see that it will plateau and level out. And yeah, Roland, sorry, mispronounced name there. Roland, when your O2 reading varies randomly, collect a minute or two of data and then take an average. Exactly. That's the other thing I highly recommend doing, especially when students have trouble, especially younger students. I find this common with middle school students. And freshmen and lower levels in high schools, they really want to have that perfect number. And it drives them crazy when they can't get a perfect number because the values are constantly changing. So if you take like 60 seconds of readings and then average that, that's a great way to get a good value. Brett, does bright ambient light negatively affect the optical probe readings? Yes. So with the BTA version, we have found that specifically, yes, light can affect these. And that is why we started shipping it with that black light guard on it. And it's really specific. We found it very specific to wavelengths of light and the position of the light. The light actually has to be shining like directly on the tip of the probe. The Go Direct probes were redesigned a little bit to avoid that problem. So that we actually have not seen that problem with the Go Direct versions. If people have, we need to know. But we have the same kind of grooves on the Go Direct one, so that same light shield will fit them along with that same metal guard for field use. Will also. But honestly, if the light is affecting the readings, it's very obvious. It's not a subtle change. It's quite literally we see a spike come up and then come down. And that's where we find that worrisome part. Okay, so sensor care. The great thing about the probeware is it's pretty easy to store. You don't have to really worry about storing them in a specific orientation, like a pH probe or a oxygen gas probe. If you have the electrode style dissolved oxygen probe, that one we see a lot of problems with because people accidentally store it wet. That probe actually needs to be stored dry. You need to make sure to empty out that filling solution, that electrochemical filling solution that goes in the tip, and dry out as much as you can, because storing it wet can cause corrosion and actually can cause it to eat through the membrane on the tip of that probe. With the optical versions of the probe, both of them have a sponge in the tip here that if it dries out, it's okay. They don't have to be stored wet. What I like to say is just a little moist is perfectly fine. So you want to make sure that that sponge stays hydrated. If it dries out over the summer, that's totally fine. What I recommend doing is just going ahead and soaking the probe directly in water for 24 hours and then saturating that sponge. And the reason we have that sponge and why we store it in this humid environment is actually to get the membrane primed and kind of ready to go so that it can easily and more quickly respond and take readings. So that's why if it dries out, it's not the end of the world. It's perfectly okay. Now, for calibration on the electrode version, you do want to calibrate that fairly often. If you're doing multiple readings in 1 week, I usually tell people calibrate it once, and then just when you're done with your reading, keep the tip on with the electrochemical filling solution in there, and just keep it in a beaker of distilled water for that week. And then when you're done with it for the week, empty it, clean it out, things like that. With the optical versions, there is no calibration, but there is what we call a reset. And the reset is kind of what I was talking about, where you want to bring them all kind of back in line with each other reading wise. So with a reset, the process is you actually take distilled water and fill up the cap until the sponge is actually submerged in distilled water. And then you want your probe to actually hang or sit upright for about 1 minute. Longer is better, but what happens is that moisture is going to increase the environment in here so that it's 100% humidity. And with the BTA version, you would plug it into your LabQuest 2 or your LabQuest Mini, and you're going to need the world's tiniest paper clip to go in and press down the reset button on here. And you should have the switch put on %. And as you're looking at your interface, you hold that reset button down until the readings drop to 0. Once they drop to 0, you release, and it can take a couple minutes, but the readings will then come back up to 100% or around, and then just let it sit for about a minute to kind of fully equilibrate, and then you're good to go. With the Go Direct version, this is all done in software. So it's the same thing. There's a little sponge in here that you fill water up to the top of. The key is you don't want to have the tip of the probe submerged in water, because the water you're putting in there isn't necessarily saturated. What we're creating is a humid, saturated environment. And then I'll show you when I kind of pull up GA here, and I can show you some of the things I was talking about, and I'll show you how to do that reset there. Tip replacement. So the electrode version and both of the optical versions do have tips that age over time. The electrochemical one or the electrode one, I have not found that it has to be replaced every year. It's usually until it tears, or it might get a micro hole in it. And usually you can tell it's not working very well anymore because your calibration doesn't work, or you calibrate it and then the readings just are all over the place and not correct. That's a good indicator. With the optical probes, the tip is warranted for 1 year. It's going to last longer than 1 year unless you take that probe tip and scrape it along rocks at the bottom of a stream or in the ocean or things like that. Again, kind of the indicator of when the tip needs replacing is if your readings aren't looking normal, they don't make sense anymore, or you're constantly having to reset it all the time and that reset is not sticking to it. The other thing I've noticed is the tip of the probe starts to almost turn a little gray, and that's a signal that that tip does need replacing. Some of these tips, though, I've had on there for 4+ years and they still seem to be reading just fine. So I don't think it's necessarily an age thing with those tips. It's more kind of a constant use thing. And another question we often get is, how can I properly clean these? So a lot of times I just rinse them with distilled water and they're good to go. If I'm doing data collection in a really mucky eutrophic pond that is like lots of algae, super stinky, probably tons of bacteria in it, what I probably would do is when I get back to the lab or to the classroom, I would do kind of a 10% bleach rinse. So I put the 10% bleach in a beaker and just do a little bit of a swirl for about 60 seconds of the probe, and then rinse it off with distilled water. Good way to clean it. It is plastic, so don't use acetone. Don't use any organic solvents that can melt plastic. That would be really, really bad.
Hey, Colleen, there is a question in chat about storage, and is tap water okay for that?
Is tap water okay? I think tap water would be fine in there, as long, I mean, I've done it in a pinch. Distilled water in theory is the best because tap water does have a little bit of salts in it. So as it evaporates, it's going to leave the salts behind. That's usually why we recommend distilled over tap. But in a pinch, tap is totally fine. Okay, let me launch graphical analysis here. And where did my graphical analysis go? There it is. All right. So I just kind of want to show you what the dissolved oxygen probe Go Direct version looks like, because Go Direct is very different than our normal LabQuest sensors. So I am doing sensor data collection. So I've turned my dissolved oxygen probe on, and you can kind of see it's blinking red. So it's displaying its signal. And we are going to look for all of the probes. You can see I'm in the office, so every single Go Direct probe that it sees here. I'll look on the back for my code, 0011. So when I connect my Go Direct probe, it automatically is set to read dissolved oxygen concentration. If I click here where it says sensor channels, this is where we get that big difference between a Go Direct sensor and a non-Go Direct sensor. I can actually turn on multiple channels here, and I can turn on all 5 if I want to get my readings. And then I click done. And so when you turn on all 5 channels, you can see it gets a little messy here. So often what I like to do is just go and look in meter mode. Ooh, we're going slow. I'm going to turn off my graph. And so I have all my meters going here. So I've got my dissolved oxygen concentration, saturation, temperature, pressure, and then DO salinity is that channel I was talking about, that if you have a specific, if you're doing saltwater measurements, this is where you want to go. And say, I'm like, I wonder if my probe's responding. So one thing I can do is I can actually look at my probe here. I cut my hand and I can actually see blue and red lights blinking. So that tells me it's working. Then if I put my hand over it to heat it up, you should see the dissolved oxygen starts to go down and my temperature readings start to actually go up here. And then same thing with pressure reading, my saturation. Pressure is going to stay the same because the pressure is in there. I think if I like create a vacuum, like I can't even, oh, there we go. If I cover it up and press on it, I can cause that to change as well. So that's one really good test if you're worried that your probe is not working or responding. The other, like I said, would be putting it into a beaker with bubbling, with an air bubbler in it. So I'm going to put this back in and say I want to recalibrate, or what I also call reset my sensor. So I go over here to DO concentration down in my lower bar here. I'm going to click on that and then I'm going to click calibrate. So what's great is that we have some instructions set in here for you to look and follow to actually walk you through that process of properly calibrating it to get the probe back in order. How often you should do this? Honestly, I don't do it very often if I'm doing just basic like photosynthesis measurements. If I'm going to go out and do water quality testing where I really want defined, distinct values, then I'm going to calibrate it before I go out. That should be for any probe that you're going to use. pH, conductivity, things like that. If I am going to be measuring in salinity, what I want to do here is go to DO salinity, calibrate, and calibrate's not the correct word here, but what I can do here is actually enter if I need to know what the salinity of my water body is. So I might know, okay, it's 28 ppt. So I adjust that, I press keep, and then done. And if you noticed, my DO salinity reading changed here because it's altering that reading from up here based on what that concentration of salinity is. All right. All right, so that kind of comes to the end of things. Are there any other lasting, dying questions people might have about dissolved oxygen or specific experiments dealing with dissolved oxygen? We've got a few minutes left here, so I am your guru to answer these questions. And this is when I wish we could have people live in here so I could actually like see faces and interact. I don't see anything coming in. Oh, wait. Did one come in? Okay, so we got two of them. Do you still sell the calibration solution for the old DO probes? Yes, we still sell the calibration solution and the filling solution for those probes. So you can always have those present. And then Chuck asked, how often is the membrane replaced? So on the old school DO probes, that membrane, I usually would replace it if I started noticing the values weren't running exactly how I expected them to be. It can vary anywhere from 1 to 5 years. It's quite variable and depends. And the same thing with the optical ones. We don't have an absolute value like we do for the ISEs, the ion selective electrodes, which we know they have a specific lifespan. These, it's kind of variable. It depends on usage, it depends on care, a lot of different factors in that. Yes, Roland, dissolved CO2 probes. So we have looked into the technology for dissolved CO2. And for people who have tried to use our ion selective electrodes and know how difficult those can be to use, a dissolved CO2 probe is even more difficult to use than those. So what I tend to recommend people to do, and I actually did a activity back in last November that we have a recording of a webinar about acid rain and ocean acidification. And for that, I actually tend to recommend using a pH probe and kind of measuring CO2 by the relationship of carbonic acid forming in the water due to the introduction of CO2. So that's where I tend to recommend people look for if you're looking at CO2 concentration. It's a pretty close relationship. It's not perfect, but it's one of those, it kind of helps at least get that kind of thought process and measurement in. All right. If you have any questions that might come up, yeah, exactly. It would work if there's no buffers present. If there's buffers, it's not the best. So it's kind of one of those, like I said, it's not the ideal, but it's kind of close enough for what we can do. If you have any other questions that come up, please don't hesitate to reach out. You can contact me at biology@vernier.com. I hope you enjoyed today, and if you and like I said, reach out. We're happy to help you with any questions you have or any further troubleshooting you might come across. That's what we're here for. We're here to help you out and make your lives easier. So thanks again, everyone, for attending, and I hope to chat or email or talk to you soon. Have a fantastic rest of your day.